Hey everyone. I'm really happy to be here today and discuss to you a bit about multi-objective reinforcement learning. I feel this is too loud. Okay. So what I wanted to do today is start with a bit of a discussion, let's say somewhat philosophically around the topic of rewards and reinforcement learning in general. And afterwards also show you my perspective, let's say, on modeling decision-making problems, namely by taking multiple objectives into account and go a bit into the theory of what that actually entails. Is this better? So let me start by just saying that I believe, and I hope you agree with me, that we do operate in a world where at every step when we need to do something or we need to take into account multiple, call them factors, aspects, objectives. And not only that, we are not alone. We are always surrounded by others, and their behaviors and interacting with them also impacts on us, on what we do, on how we decide, right? Um, so just to give you a few examples, if you want to decide with your group of friends to go out, choosing a restaurant is a multi-objective, multi-agent problem. Whenever you are trying to collaboratively solve some project at work, you are doing exactly the same thing. One of the most challenging multi-objective problems in today's world, maybe, life-work balance, right? It's, again, a multi-objective, multi-agent setting. And I can give you, of course, more complex examples like traffic systems, managing electricity grids, or any resource management problem in general, or medical settings where we want to come up with treatment plans for patients that trade off nicely between side effects but also efficiency. Logistics, manufacturing settings. So, in general, naturally, complex real world decision making problems are multi objective in nature and most of the times involve the interests of more than one stakeholder. So, notice that the commonalities of everything I'm introducing here is, of course, the idea of decision making, right? The process of evaluating alternatives, um, and selecting the best course of action in accordance to what we deem to be the best outcome, right? Um, for everyone in this room, since we are at the control theory and RL workshop, I suppose um, we are used to designing autonomous agents for these type of settings. So I don't need to introduce or spend too much time on this uh, framework, reinforcement learning, learning by interacting with the environment, trial and error fashion. And the goal is to maximize our discounted sum of rewards. So let me get a bit into the philosophical aspect here about what intelligence is and how people have looked at in this reinforcement learning context. So perhaps you're familiar with McCarthy's definition of intelligence. I will start from there. So McCarthy was saying that intelligence is the computational part of the ability to achieve goals in the world, right? So grounding, very much grounding this idea of intelligence to achieving goals. I am sure everyone has heard about Rich Sutton and his reward hypothesis. So Rich was building on top of McCarthy's definition of intelligence, and he was mentioning that in his reward hypothesis that the purpose or goal of any rational agent can be well thought of as the maximization of expected value of cumulative sum of scalar rewards, right? So intelligence equals achieving goals. In order to achieve goals, you can think about achieving goals as maximizing a reward signal, right? So putting this together, you had the somewhat recent, I think it was 21, reward is enough paper, right, of Silver et al., which basically put these two together, and they were implying that succeeding at building AI or intelligence, it suffices to basically succeed solving RL. This was a very, very general paper. They never actually discussed any formal definition of under which condition this holds, right? This was just trying to give or ground a bit the theory about intelligence. But I don't know if you're familiar with the discussion around this topic. Um, there was a lot of subsequent work trying to understand, ground, or argue against the reward is enough hypothesis. So, Bowling in this settling the reward hypothesis paper, highly theoretical, he tries to come up with the exact axioms that completely specify the implicit requirements on the goals and purposes for which the reward is enough hypothesis holds. You can look, if you're interested in this, have a look. But of course, there were also work which explained under which conditions reward is not enough, right? Under which conditions, so you can see already they were looking at expressivity when it comes to multidimensional Markov rewards or non-Markov rewards representations. So clearly, what I'm trying to say here, there are settings in which scalar rewards are insufficient. And we have our own work that contributed to this conversation, where we were mentioning that even in an ideal world, where you do have a nicely designed reward function that might give rise to highly complex behavior and skills, it's still somewhat undesirable to stick with scalar rewards because we are missing the users of the system. Humans are still present in this world. So if we do want value alignment with humans, scalar rewards will never be enough. So just a few ideas here and there. If you are ever interested in exploring this, I leave you a few references. Now let's look at reinforcement learning as a whole. I don't know if you have read the Welcome to the Era of Experience from Sutton and Silver. I don't know who's familiar with this recent paper. A couple, okay. Hope I'm not going to bore you too much. So this is just a graph, a plot from their paper explaining a bit the attention of RL over time. I don't know how many of you remembered the famous Ian LeCun talk from Europe's 2016, right, where he was mentioning that if ML, machine learning, is a cake, then in his opinion, unsupervised learning was the actual cake, right? Supervised learning was the icing, and RL was the cherry on top. So that's where you can kind of see the dip at the beginning of 2016 of RL. However, we all know what happened with DeepMind's AlphaGo, right? That's where the attention of RL really increased. And that's what they classified as the era of simulation. So we had very nice script simulations that allowed us to really boost the performance of RL. Era of human data, agentic, Gen AI, right? This is where we are kind of at now. That's when RL kind of dipped. And afterwards, now they're predicting this type of era of experience where we can finally start taking what they call now agentic AIs, put them in the real world, and learn from some actual grounded streams of experiences. So, but how is this usually done? And I think in the previous talk, there was also some mention of this on how do we design currently reward functions in our system. And here in this slide, I'm trying to summarize a bit the process. At least I've gone through it a few times. You can tell me your experience. And by the way, if you have questions at any moment, feel free to interrupt. So in the normal design process, what we usually start with is, to the best of my knowledge, design some reward function, train our agent, and then look at the outcome. Is it good? Is it bad? Well, usually at the start, it's not that great. So what we need to do is iterate a few times through these steps until we get something that looks like, something that looks good to us. Of course, this is wasteful and time consuming because each trained agent and reward function is basically discarded. But I also challenge you here to ask, when you do have this scalar reward design process, what you're also implicitly doing is baking some form of trade-offs into the process. And depending on the application you would like to deploy this behavior, and are we actually, like designers of the system, the best people to decide on these trade-offs? Maybe they would have been a better balance among the considerations and how to take them into account. So it's becomes really important to discuss with the knowledge experts of that domain, and how to basically plug in their knowledge into the design of the system. So this brings me then, with hopefully some strong motivation, to this potential um, alternative multi-objective reinforcement learning. Multi-objective RL is not new, right? It's from '98, almost at the same time with actual RL. So it's quite a straightforward, natural, I would say, extension. The main difference is the definition of the reward function. So if you know MDPs, multi-objective MDPs will be defined on vectored valued reward functions, where each component of your reward will give you the signal or the performance on one objective. So I don't know if you want to think a bit about it. If you are in a manufacturing setting, you will care and track separately your performance on, I don't know, material costs, the energy consumption, CO2 emissions, and so on. So notice that in my example here, the reward signal is derived from clearly grounded signals coming from the real world. And this is the main advantage of multi-objective RL, because it becomes very difficult to start engineering or trying to put together in a single unit these type of signals in general. So I really hope that by now you do have an intuition on why it would moral as a framework can help us a bit be more beneficial in terms of adhering to some external users or stakeholders. So let's get a bit more technical and understand a bit the setup. Multi-objective MDPs, you have the usual set of states, set of actions. From MDPs, your transition function, discount factor. But now the main difference is your vectorial reward function, defined on RD, with D being the number of objectives. You can easily see this is a generalization of MDPs, because if you set D to 1, you collapse back to the MDP model. What are the consequences of this difference? The agent still needs to learn to behave according to a policy pi, a probabilistic mapping from state actions between states and actions. However, the value function now, right, our usual expected discounted sum of rewards, is now also vectorial. Immediately, now you can see that our value function can no longer supply a complete ordering over our state actions. There will be settings in which, or states in which, for some objectives, the value function is bigger than for policy pi than pi prime, but not in other dimensions or objectives. So in order to make decisions, select actions during policy learning or execution, right, the reward needs to be scalarized or combined in some way, or we need to come up with other type of clever operators in order to overcome this challenge. So let me introduce you one very important concept of multi-objective reinforcement learning, namely utility functions. And before I actually introduce the mathematical definition, I was actually also very happy to see that in the latest paper, The Era of Experience, Silver and Sutton discuss the following segments, although they do not call them utility functions, but I'll take it. So they mention that the pursuit of a single reward signal does not on the surface appear to meet the requirements of general purpose AI that can be steered reliably towards human or user desired behaviors. So it was very nice to see that somehow, when taking user desired behaviors into account, Silver and Sutton also perhaps do not believe that scalar rewards are enough anymore. They mentioned that the idea is to flexibly adapt the reward based on grounded signals in a user-guided manner. So for example, they mentioned the reward function can be a neural network that takes the agent's interactions and users, well, environment input and users into account, and then outputs a scalar reward, right? So basically, we can select and combine reward signals in a manner dependent on the user's goal. Well, in our framework, this is literally the definition of utility functions. It's a scalarization function that maps user preferences over the objectives to some scalar value. Of course, I will have to admit, this is not easy to define, elicit, or learn about. But this is the mathematical tool that can allow us to trim down our problem. In a multi-objective decision-making modem setting, the usual assumption we make about utility functions, mathematical assumption, is monotonicity. We assume the utility function to be monotonically increasing, or in other words, we always want more in each objective. This also allows us to ground solution concepts that I will go into in a second. A consequence of looking at the problem through this utility function perspective of scalarization is the fact that now we have the choice on how, or the question on how should we apply the utility function to our vectors, value vectors, right? So remember, this was the quantity we were trying to scalarize, and we want to plug in that u. Well, let me first give you the intuition of the two mathematical ways in which you can do that, and then hopefully explain a bit the intuition between when should you choose for one or the other. So first, we have the option of what we call scalarized expected returns. Intuitively, what we are trying to do is, or what we are trying to optimize under SCR, is the utility over several executions of the policies. We are deriving our utility over multiple policy executions. The other end, or the alternative, is what we call expected scalarized returns. And here, this is the correct criterion if what we are interested in, or what allows us to derive utility from, is individual policy executions. So let me just give you the mathematical formulas to immediately see the difference between them. Scalarized expected returns, I scalarize, u is there, and then I take the expectation over my returns. While ESR, I first take the expectation, and then the scalarization is applied immediately over the sum of discounted rewards. Why are these not equivalent, or when they are not equivalent? Well, when u is nonlinear. And we do have a relationship between them depending on the properties you might have. You might be familiar with Jensen's inequality. But in many cases, if u is nonlinear, you should be careful on which one you are using. You can't say one is correct and one is incorrect. No, it just really depends on your use case. I always try to find some examples maybe to accompany this. So if you are in ESR setting, for example, in medical domains, you want policies that give you that optimize your utility for every application. For every policy you apply, for every patient you will apply the treatment on, right? You want to maximize the ESR. You do not want to actually apply SCR in medical domains because you do care about each patient individually, right? In SCR cases, you need to be able to just do multiple policy applications, in the sense that if you have some long-term portfolio optimization for some, I don't know, buying many properties, and you want to maximize your revenue over a long period of time, just the policy of purchasing can optimize over multiple policy executions, something like this. So you need to be able to care about it in that way. Okay, so it becomes a bit more complicated, but what I should mention is, again, we might not always know you, or you might not be available. So yeah.
Why do each individual
Yeah, I was also trying to think about that. When would you like to do that? And when would it make sense? And what are the implications of scalarizing at every time step? And I don't yet have a grounding of whether that makes sense or when it makes sense. But that's also something I would like to look at. Yeah, for now in the literature, you have these two options. And actually, I will tell you that SCR comes more natural under RL because we are just so used to doing the expected sum. Um, but it doesn't always make sense in practice. So actually, you will see a lot of developments in theory under SCR, and ESR is understudied. We don't even know the exact solution concepts under it. But yeah, yes, thank you. That's a really good remark. Okay, so let's quickly discuss also a bit some decision-making, multi-objective decision-making scenarios. Um, what was usually done up until some point is this loop. You start from your multi-objective MDP, you have your planning or learning algorithm, and what results, so they usually assumed U unknown, is an entire solution set. Why? Because if you have no way of scalarizing, then the optimal thing to do is actually provide an entire set of optimal trade-offs between all the factors you are optimizing for. In one of our works, the Practical Guide to Moral, we give a bit of a different perspective. We advocate for taking this utility-based perspective and extending a bit the view to not only look at the planning and learning phase, but to think about the entire process. Namely, okay, you will do some planning and learning, you will derive a solution set, but what happens after? You at some point will have to also do some selection phase and execution phase. So for example, two scenarios you can that this can happen in. After your solution set is derived, maybe you do have some way of interacting with your stakeholders and getting their utility function, either directly or through user selection. And then you will have to actually decide which of the solutions from your solution set is the optimal one and execute it. Of course, there are multiple settings. Even in the area of experience, they do mention users could provide feedback during the learning process, such as their satisfaction level, which could be used to fine-tune the reward. Okay, this basically describes what we call interactive settings, right? In which during the learning and planning phase, you interact with your user and you try to also guide the exploration of your multi-objective reinforcement learning or planning approach directly towards a single solution for the execution phase. Again, um, this is challenging. Not a lot of work has been done here, so it would be great to see how this can be done. Now, of course, we have so many ideas, incoming ideas from related fields. You have RL from human feedback and so on. So I think it's an opportune moment to actually start leveraging and putting all these perspectives together. Of course, another one I will add that wasn't in our practical guide is this one, right? This looks perhaps more similar to what we are seeing nowadays in the algorithmic setting. Maybe you can have some algorithm that derives some base raw solution set, right? It doesn't need to necessarily be optimal, but then using some user preference elicitation or something like that, you can start doing fine tuning during the repeated selection and execution phase, right? So then you will have, we are going into more this continual learning type of settings. What I'm trying to basically say here is it's a quite flexible framework. Um, it does accommodate a lot of scenarios. So let's also quickly discuss about solution sets a bit. What exactly are those? Uh, you have here on the left an entire characterization of them. The most general one under the assumption that U, the utility function is monotonically increasing, is the Pareto front. The PCS, the Pareto coverage set, is the minimum amount of values that cover the Pareto front. And then you have your convex hull, and that's the, basically just remember Pareto front and convex hull. Pareto front monotonically increasing U, convex hull, you assume U is linear. So because I will later need this a bit more in detail, I don't know if you're familiar with Pareto dominance relationships and Pareto fronts. So let me just quickly introduce this. A Pareto, so a vector is called Pareto dominant or dominates, Pareto dominates another vector. If it's at least equal in all objectives and greater in at least one, you have there a little example. 1, 2 Pareto dominates 1, 1. Strict Pareto dominance is when you're greater in all dimensions, right? And the Pareto front then applies the Pareto dominance relationship pairwise to all the values. And the Pareto front is formed by the set of pairwise non-dominated policies. It looks like this. So for example, I'm showing here on the right side a maximization problem in 2 dimensions. Notice that the Pareto front can also have irregular shapes. I will tell you that the shape of the Pareto front is impacted by multiple things, including your policy class. So if you are allowing deterministic policies versus stochastic policies, it will make a difference on the shape of your Pareto front. So that's very important for a bit later as well. Convex hull looks like this, right? It's in a convex hull, it is sufficient. For example, I can tell you already, if you allow for stochastic policies, then the convex hull is sufficient as a solution set. So it becomes more, it's less difficult, let's say, in that case. The most challenging, interesting setting is when you do need deterministic policies. And I will also mention that in many real-world cases, you do have the deterministic policy requirement because they don't like to just throw dice in certain settings. They want to know exactly what your algorithm will do in a certain state. A bit of information on optimality in MOMDPs. We already have a result from the 80s, White's paper. I put it over there. That mentions that in MOMDPs, if you consider deterministic policies, then non-stationary or memory-based policies may Pareto dominate stationary ones. In other words, in MONDPs, if deterministic policies are required, we need to start looking into memory-based policies in order to get optimality. This is a really big difference with MDPs. How does this go in practice? Well, that's why in many algorithms, multi-objective RL algorithms, if you look now in the literature, you will notice that what they do, they augment their state information with accrued vectorial reward up until that point. And that's the reason. They are basically creating this augmented or memory-based policies to ensure optimality of the solutions. It's based on that reference if you're interested. Just a few very practical things. If you got curious about moral, look into MO Gymnasium and moral baselines, hands-on available collabs, notebooks as well you can play around with. And if you also are interested in multi-agent by any chance, there's also MomaLand, also a Farama library that of benchmarks for multi-objective, multi-agent problems. Okay. The next part I wanted to talk about today is also one of our latest general purpose multi-objective reinforcement learning algorithms, just to give you an idea of how it looks like to optimize for this type of settings. So I will discuss next iterated Pareto referent optimization, IPRO. This is a work we just published at AMAS 25 last month. So I'll do my best to go into it. The first idea to present before introducing IPRO is this idea of decomposition. It's as easy as it sounds. What we want to try to do is decompose a multi-objective problem in a sequence of single objective problems, right? That we can hopefully solve in a more efficient manner. Afterwards, we can recombine the obtained solutions and obtain our multi-objective final solution. Why is this nice? Well, of course, that it allows us to immediately link any progress that is done in single objective RL with multi-objective RL, right? And it's not new. It's always done in multi-objective optimization. And so far, you will see it in most multi-objective RL algorithms, but with linear preferences, so linear utility functions. So our question was, can we use decomposition, but in general Morse settings? Namely, we do not assume linearity in our utility functions. Just a small repetition in case you forgot in the meantime what MOMDPs are, but we are starting from multi-objective NDPs. And what we were also after is having some form of guarantees. So we were trying to obtain a provably correct solution set under any given policy class and general preferences, right? So we wanted to also be able to retrieve deterministic as well as stochastic solution sets if that's the requirement, but also function under any utility function class. So this is what IPRO manages to achieve. General at a glance idea of IPRO is we will be decomposing our multi-objective problem in a sequence of single objective problems. And this single objective problem will be solved by calling what we named as a Pareto oracle, namely a modified, let's say, scalarized RL algorithm. And how do we scalarize it? Well, we use a special type of nonlinear scalarization function. I will get to it in a second. I don't know how much time we will still have, but basically underneath the surface, our Pareto oracles, we played around with a few, are just DQN or A2C or PPO type of algorithms. And just to give you a bit of an overview on the capacities or capabilities in comparison to other existing methods over there, we do have convergence and runtime guarantees. We can cope with nonlinear preferences, and we can function in any type of MOMDPs. So we are really happy about this one, let's say. So let's break it down. IPRO starts with one big phase, establishing the bounding box of our search space, or the space in which we are looking for solutions. And in phase 2, we will do this iterative querying of our Pareto oracle with a referent. A referent is just one multi-objective or one value vector. Our Pareto oracle will return us a solution, and that's using that solution, we will start cutting away space in a, of course, strategic fashion. I will go into it in a second, step by step. So the key idea is to try to, at every iteration, get a new solution from our Pareto oracle and to leverage that to reduce the search space in which our solutions can reside. How do we build our bounding box? We simply just optimize for each objective. So if we are I will use as a visual example the 2D case. So we start by maximizing fully for x-axis or y-axis. And let's say we get to solutions, V1 and V2. This allows us to construct this bounding box. So we just add two, the ideal and the nadir point, right? The maximum over there, the ideal point, we might not ever reach it. That's an imagined point, let's say. Same for the nadir, that gives us a lower bound of our space. And it's very nice because we also have guaranteed lower bounds for our Pareto oracle, right? So then we start querying using VN, that's our lower bound, and we start querying our single objective algorithm. And let's say we get in return V3. So this point over here. Yeah. This is the return Pareto optimal solution. What can we do with it? Well, this allows us to basically start reducing our search space in the following matter. Perhaps it's obvious, I don't know. On this side of the shaded area, since we already have V3 returned as a point, this area is dominated with, we can throw it away. And we also, so that's the dominated set. And on this side, this will be the infeasible set. If we would have had solutions in that area, they would have been returned. So theoretically, we can also remove the infeasible set. Of course, this also depends on how strong and how correct uh, is our Pareto oracle. If it will make mistakes, we might end up throwing spaces that still contain solutions. We need to be careful on that. In practice, we know that deep learning algorithms, like the ones I mentioned, are not perfect. So we do need some backtracking mechanism to prevent us from suboptimal Pareto oracles. And just to understand a bit how this works, IPRO is just keeps track of lower and upper bounds, the points you see there highlighted in green and blue. And it's just a matter of selecting in an efficient way the next lower bound point to query the Pareto oracle. So we just iteratively do this. What I should also mention, so for example, if the next point you would see there is V4, it allows us to extend our dominated set and so on, but also finish completing sections like the orange highlighted over there. It's just a matter of keeping track and updating correctly the lower and upper bound sets. Because we keep track of these lower and upper bound points, we do have some very nice properties and also guarantees during learning. So the upper bound, we have guarantees on what is our current upper bound on the distance to any remaining Pareto dominant solution. Visually, I hope you get an intuition on that. And we have also shown that this reduction process monotonically reduces the remaining search space and allows us to converge to a tau Pareto front. And that's the important part, of course. What is tau? It's a user-defined tolerance. This is what we managed to achieve. What I have given you so far is a 2D intuition, but IPRO works in n-dimensional settings as well. But for the 2D part, we do have we can do some simplification. So we have a dedicated algorithm for the 2D case that works really well. It becomes, of course, way more complicated in n-dimensional spaces to keep track of the lower upper bounds and do the updates correctly. Now let me go a bit more into details about the Pareto oracles. Of course, what we were interested more in showing is that deterministic memory-based case. So if we are required to return deterministic policies, how can we start constructing a Pareto oracle for that setting? And it's an NP-hard problem. But we can use, of course, deep reinforcement learning. We just need to be careful on how to construct this to keep it still principled and correct. So what we have worked on, what we came up with, is using this augmented Chebyshev scalarization. I decided to not go into the functional formulas of the Chebyshev scalarization. It has just nice properties that can allow us to scalarize our problem and get guaranteed results that are in accordance to our requirements for IPRO. And how do we do the memory-based part? The same as it's usually done. We just augment the state space with the accrued reward trick, like I explained earlier, in order to obtain this deterministic memory-based policies. I will, of course, there's always a results slide, right? But what I wanted to just give you as main takeaway for IPRO is that we can tackle basically the previously unsolved settings while still reaching competitive performance compared to algorithms that either assume linearity or just more domain knowledge in general. And what we also notice is that a lot of the benchmarks existing in multi-objective RL actually do have convex hulls as solutions and things like that. So there's also a bit of a need nowadays to update a bit our benchmarks to make them a bit more complex. I think we reached a point where we can start tackling more complex settings. Okay, I'm almost at the end. So what I wanted to also end with here, I know it's a more of a theory type of workshop and setting, but what I sketched here is what you could see as or call as a hybrid type of collective, right? This is kind of a very simplified sketch of our world. We can look at it as well, of course, a multi-objective, multi-agent system, right? You can see in the middle the type of usual RL loop-like interactions, where on one hand, we also have artificial agents. On the other hand, we have humans, and they will and have already started existing, coexisting, and interacting with each other, right? So there are so many elements that need to go in for having such a functioning collective, right? You can think here about theory of mind type of thing, decision delegation, preference solicitation, because you can also have settings in which agent will represent their users and things like that, right? So while AI comes and starts being more and more embedded in our day-to-day life, it's of course more and more difficult to understand the outcomes and the dynamics of such a system. So my final, let's say, call to action would be really uh, always keeping an open mind to, um, let's say, inter and transdisciplinarity, because we can always find connections and we will need to start integrating multiple type of perspectives in order to reach solutions in these type of settings, and solutions that are safe, value aligned, transparent, reliable, etc., etc. um, just final thing, if you are interested in multi-objective settings, we are always running a yearly multi-objective decision-making workshop. This year is at ECAI. So if you have any work on this, I just wanted to let you know about this potential venue. And with that, thank you for your attention.
Does it work? Okay.
Yep.
So thanks for the talk. So in RL, there's typically training RL agents, right? Often it's a lot of variance, right? You might not always kind of find even a good solution, right, to basically the Oracle problem that you've described, right? Also, you might have stochasticity in the NDP, right? So there's noise and the rewards anyways. So kind of how do you deal with the stochasticity that results from that in making the decisions about the Pareto surface? Can you elaborate a little bit on that?
Yeah. Well, it does reduce to the normal MDP, the normal reinforcement learning problem, right? So it will work as well as it works in that case. And this is we do not create any novel algorithm. It's really the usual. Well, now it's no longer DQN. Now it's trended to use PQN or PPO or SAC or so on, and it will really work just as well as that one does. What can usually and what usually happens is that after certain iterations, we might end up finding a point in a region we had discarded. So what we do in that case, we really just keep a history track of everything we have found. So then that signals, okay, there was a mistake. And then we backtrack a bit and redo the update and discard process. We correct it, basically. Yes, and this is how currently we deal with the fact that we do not have guarantees on single objective RL algorithms. Yeah.
First time using the box. This is really cool. Since the title of the workshop is Control Theory and Reinforcement Learning, I want to bring a question from the control theory side. Especially in the context of the Pareto problem that you mentioned, is it possible for these objective functions to be wildly disparate that you simply might not have a solution? Like, for instance, a worst case, right? Which is something that happens all the time in the context of control theory, where, let's say, for instance, you're looking at an objective function totally complementary to the kinds of like loss functions that you might be considering. For instance, stability and optimality are sometimes two sides of the coin. And when you're trying to go towards stability, you simply have to discard a lot of the optimality centric stories. So is there a worst case boundary that you can articulate using your tools so that you can say, okay, when I go beyond this point, I simply cannot satisfy both of these objective functions?
That's a really interesting question. That's something we want to look at right now on trying to be a bit more flexible, and also actually while learning, we would like to interact with the user and give them the opportunity to see like, hey, if you are this strict on this dimension, and this will cost you this part of the search space, right? That would be ideal, because otherwise, if you start from very fixed constraints or preferences, we might end up with very little number of solutions and a very irregular, very hard to explore search space, right? So ideally, we would like to have these type of very flexible tools. We are not there at all yet. Yes, for sure. But yeah. Thank you. Thank you for your question. In general, maybe another interesting thing I can tell you that I didn't discuss multi-objective, multi-agent in this talk, but when you also have multiple agents, each with different preferences, what will happen is that literally Nash equilibria might not exist anymore, because we cannot reach any equilibrium, any agreement. I will always want to pull in another direction than you, right? So it becomes really interesting. Yep. Thank you.
When you said it is tau Pareto optimal, so what is the tau or how you measure tau?
Yeah, so it's a user-defined tolerance. It's a number of the error you are okay with achieving.
Number of like policies which are Pareto optimal, but I didn't identify.
Yeah, so it would be like if this is the Pareto front over here, and these are our upper bounds, it would really be a difference in objective space of how far are you okay from being from potential solutions we haven't found yet, right? It's really the maximum distance between any of our Pareto points, so V1, V2, V3, V4, and the blue points you see here. But that's an interesting thing. How do we ask users to give us a tau? Because it will also have a different meaning in different settings, right? And I have to admit, we do struggle with scalarization in this setting, because each objective can exist on a wildly different scale. It depends on its physical meaning. So how to meaningfully interact with users, show them this type of visualizations, is still very much an open research question. Yeah.
And one more question is like, do you have some kind of, so if I have, let's say, a Pareto oracle that has certain amount of, let's say, accuracy or precision, do you have the number of iterations, upper bound on number of iterations you need?
Yeah. So we will converge in a finite number of iterations. We have a full workout of that. However, we still remain exponential in the number of objectives, which has and might always be the case, unfortunately, for this setting.
Okay.
Yeah.
Thank you.
Thank you so much.